Darkness ruled the universe for millions of years. This was the cosmic graveyard, a dense fog of neutral gas that swallowed all light. Then, roughly 100 million years after the Big Bang, the first stars flickered on. This pivotal time, known as the Cosmic Dawn era, fundamentally changed reality. It is the oldest, most inaccessible epoch of our universe. Scientists call this the reionization epoch, the moment the cosmos cleared its throat and became transparent. To understand how we went from utter blackness to the light-filled universe we see today, we must solve a series of profound questions. We are going deep into the scientific archives to uncover the 25 most mind-bending, unsolved mysteries of the cosmic dawn. You will learn secrets of cosmic structure formation that govern every star and galaxy in existence. We are talking about cosmic giants so pure they were made only of hydrogen and helium, and supermassive black holes that should not have had time to form. Using powerful tools like the James Webb Space Telescope and massive radio telescope arrays, we are starting to peer back into this seemingly impenetrable darkness. Get ready for a journey through mind-boggling scale and incredible cosmic puzzles. What aspect of the universe's earliest moments do you think is the most important to solve? The most fundamental puzzle of the cosmic dawn era is exactly when the lights turned on. Scientists trace the universe's transition from dark, neutral fog to the clear, ionized plasma we see today, a process we call reionization. Common sense suggests this must have happened quickly, like flipping a switch. However, current observations tell a very different and much stranger story. We use two main windows to look back into this time: distant quasars and the cosmic microwave background radiation, or CMB. Trouble starts because these two windows give us conflicting timelines, suggesting the process might have started earlier than we thought, or ended much later. For example, light from those ancient, unbelievably bright beacons called quasars shows that the universe was largely transparent, or ionized, by the time it was about 800 million years old. But the CMB, the echo of the Big Bang itself, suggests reionization must have been well underway much earlier. The conflict centers on a measurement called optical depth. Think of optical depth as a way to measure how cloudy the universe was. The deeper the optical depth, the more scattering occurred, which means the process of reionization must have begun very early. When the Planck satellite measured the CMB, the results indicated a high optical depth, pointing to a start time when the universe was possibly only about 300 million years old. That is incredibly early, suggesting that the very first stars and galaxies were intensely active long before we have solid observational evidence for it. If the Planck data is correct, the universe started clearing its fog almost immediately as the first stars formed. Yet when we look at the actual light signatures from that time, the evidence for widespread ionization only really kicks in later, closer to 800 million years. This discrepancy forces us to adjust the energy budget of the early universe. If reionization started so early, the sources that provided the necessary energy, the ultraviolet photons that stripped hydrogen atoms of their electrons, must have either been much more numerous or much more efficient than our current models predict. Solving the timeline of the cosmic reionization is not just about placing a date on a calendar. It is about understanding the sheer power and efficiency of the very first light sources in existence. Everything else in the cosmic dawn era flows from this single foundational mystery. Finding the timeline for cosmic reionization immediately raises a much more spectacular question. What actually flipped the switch? That leads us straight into mystery number 2, the greatest stellar ghost story in the universe, the hunt for population 3 stars. These are not just any stars. They are theoretical behemoths so perfect they contained only the primordial elements created in the Big Bang, hydrogen and helium. In astronomical terms, anything heavier than helium is called a metal, and population 3 stars had absolutely 0 metals. Our Sun, a population 1 star, has roughly 2% metals. These stellar giants were the cosmos at its absolute purest. Because they lacked those heavy elements which act as cosmic coolants, they could grow to truly staggering sizes. Models predict these first stars ranged from a minimum of maybe 10 solar masses up to nearly 1,000 times the mass of our Sun. To put that scale into perspective, imagine a single star so massive its entire lifetime was burned through in only a few million years, compared to the 10 billion year lifespan of a star like our Sun. They were incredibly hot, incredibly luminous, and their ultraviolet radiation was so intense it began tearing apart the hydrogen fog that blanketed the early universe, sparking reionization. These were the engines that powered the cosmic dawn, but here is the problem: population 3 stars must exist. They are essential to create the very first heavy elements like carbon and oxygen that are necessary for everything we see today, including ourselves. Yet, despite their predicted size and brightness, we have never been able to directly observe a single one. Why? They lived fast and died young, exploding in superenergetic supernova that left behind only theoretical evidence of their passing. The universe was still so chaotic and distant during their brief lifetimes that their light has been impossible to separate from the background noise. We only see their ghosts, the impact they had on the surrounding gas, and the first generation of true galaxies they helped seed. Detecting these magnificent, fleeting giants is perhaps the ultimate challenge in observational astronomy. They are the missing link between the Big Bang and modern stellar evolution, and until we find direct evidence, they remain one of the most compelling mysteries of the deep past. If population 3 stars are the missing engines, then their children, the first true galaxies, present an even greater surprise. Mystery number 3 tackles the surprising nature of these protogalaxies. We once thought the first galaxies were simply small, inefficient clumps of stars. In the beginning, the cosmos should have only contained tiny, chaotic systems residing within dense bubbles of dark matter called halos. They were not the grand, elegant spirals we see today, but rather messy, modest environments barely clinging together. Standard models dictated that it takes cosmic time, billions of years, for these small building blocks to merge and mature into large, recognizable galaxies like the Milky Way. But the James Webb Space Telescope has entirely upended that gentle timeline. Webb is looking so far back into the cosmic dawn that it is observing these very first galactic seeds, and what it sees is almost impossible. Instead of finding only small, expected nursery clumps, astronomers are finding galaxies that are astonishingly massive and surprisingly mature at high redshift. High redshift simply means they are incredibly distant, so far away that we are seeing them back when the universe was less than 500 million years old. These ancient systems appear to have already undergone several rounds of star formation, possessed complex structures, and were forming stars at rates far exceeding what the models predicted. We are finding early galaxies that are already the size of smaller modern galaxies when they simply should not have had the time to grow that large. Think of it like meeting a toddler who can already run a marathon. The discovery challenges a core tenet of cosmology, demanding we rethink how quickly structure could possibly form in the early universe. Did the first dark matter halos collapse more efficiently than we thought? Were the star formation processes in these protogalaxies hyper-efficient, burning through gas reserves at an unprecedented pace? The sheer mass and maturity of these shockingly ancient galaxies force us to accept that the universe got to work building huge structures much faster than anyone anticipated. We have found the marathon runner, but we still have no idea how they learned to run so quickly. The existence of shockingly massive early galaxies only deepens the central enigma of reionization. Something had to be driving the cosmic clearing process, and that brings us to mystery number 4, the crucial question of the escape fraction. Hydrogen atoms in the neutral fog can only be stripped of their electrons or ionized by extremely energetic ultraviolet photons. These photons are produced inside the newly formed stars of those protogalaxies. For reionization to happen successfully across the entire universe, those photons could not just stay trapped within their host galaxies. They had to escape into the vast, dense interstellar medium and then keep going into the intergalactic space beyond. The escape fraction is simply the percentage of ionizing photons that made this tremendous journey. Here is the conflict. For the universe to be completely cleared of its neutral fog by the time it was 800 million years old, theoretical models demand a surprisingly high escape fraction. Scientists calculate that somewhere between 10% and 20% of all generated ionizing radiation needed to make it out. But when astronomers look at nearby, modern galaxies that are actively forming stars, the observed escape fraction is usually far less than 1%. This is a massive gulf between what physics demands happened and what we see happening today. If the early universe followed the rules of the late universe, reionization would have been impossible. So how did those intensely powerful but fragile ultraviolet photons escape those dense, chaotic early galaxies? The answer likely lies in the violent nature of the cosmic dawn. One leading idea involves the sheer intensity of the star formation itself. Early stars produced fierce stellar winds, powerful outflows that could blast holes clean through the surrounding gas cloud, or interstellar medium, of their host galaxy. Think of massive supernova effectively punching tunnels directly through the galactic walls, creating temporary, low-density paths for the ultraviolet light to follow. These temporary escape routes allowed the necessary fraction of light to flood the cosmos and start stripping electrons from the surrounding hydrogen, creating the growing ionized bubbles that eventually merged to clear the universe. Finding definitive evidence of these ancient photon tunnels remains a cutting-edge goal for deep space observatories, because without an efficient escape mechanism, the universe would still be shrouded in darkness. Clearing the cosmic fog was only half the battle. Mystery number 5 focuses on why the space between galaxies is not ice cold. Beyond the simple act of stripping electrons from hydrogen atoms, the first sources of light had to heat the vast, empty void known as the intergalactic medium, or IME. Understanding the temperature evolution of this medium is absolutely crucial because temperature dictates how structures form in the early universe. If the IGM remained too cold, gas would collapse too easily under gravity, leading to structure formation that contradicts what we see today. If it was too hot, star formation would be suppressed. This tight balance is determined by the heat sources the early universe provided. One of the most important concepts in this heating process involves something called Wouthausen field coupling. This complex-sounding idea describes how ultraviolet photons from early stars did more than just ionize the gas. They also changed the basic energy levels of hydrogen atoms, forcing them to absorb and re-emit the cosmic microwave background radiation. In essence, the stellar light mixed with the echo of the Big Bang, starting a heating process within the neutral hydrogen gas. However, stellar ultraviolet light alone was not enough to raise the temperature significantly. For the IGM to reach the temperatures required by observational models, something much more energetic had to be at work: X-rays. Where did these powerful X-rays come from? They likely streamed from the accretion disks of the earliest supermassive black holes or from the remnants of massive, violently exploding population 3 stars. These penetrating X-rays could travel vast distances and efficiently heat the IGM, raising its temperature high enough to inhibit the formation of smaller galaxies. Measuring this ancient heat is incredibly challenging, requiring massive radio telescope arrays designed to detect the faint, stretched-out signal of neutral hydrogen gas from that epoch. We are essentially trying to take the temperature of the cosmos before the universe was even 1 billion years old, confirming whether those hyper-efficient early black holes were indeed the necessary cosmic heating elements. The necessary cosmic heating elements lead us directly to the greatest energy source in the early universe. Mystery number 6 asks why all the most powerful light sources seem to be missing in action. Quasars are the blazing hearts of young galaxies, incredibly luminous spectacles powered by supermassive black holes actively gorging on gas and dust. They are potent factories of the high-energy ultraviolet radiation required to ionize hydrogen, and of the X-rays needed to heat the intergalactic medium. Given their immense power, quasars should have been a major force in driving the cosmic reionization process. If they were the main engine, we should see an abundance of them, especially the fainter, more numerous ones, during the peak epoch of reionization, when the universe was between 500 and 800 million years old. Yet observations reveal a persistent and perplexing deficit. When we look back to this critical time, we find a steep drop-off in the numbers of detectable quasars, particularly those that are less luminous. The total light output from the few bright quasars we can observe simply does not add up to the staggering amount of energy required to ionize the entire universe. This leaves cosmologists searching for the missing light. Did faint quasars exist but remain hidden from our view? One leading hypothesis suggests that the earliest black holes were simply too dust-obscured to contribute significantly to the ionizing budget. The early universe was a messy place, filled with dense curtains of gas and the debris from massive star explosions. These chaotic conditions could have cloaked many faint quasars entirely, trapping their ionizing radiation inside their host galaxies before it could escape. Imagine trying to see a light bulb through a thick wool blanket. The light is still there, but it is effectively useless to the outside world. Another possibility is that the earliest supermassive black holes were intensely episodic and short-lived. Maybe they flared up violently, released a tremendous burst of energy that lasted only a few million years, and then went dark quickly, making them astronomically difficult to catch mid-flare. If the young quasars were highly efficient but fleeting, their total contribution to reionization would be diluted across cosmic time. The fact that the universe became transparent, despite this missing quasar light, strongly implies that another, more numerous and perhaps less spectacular source of ionizing photons was truly responsible for clearing the cosmic fog. If the brightest beacons were largely missing, what then was fueling the few that we did see? This leads us to mystery number 7, perhaps the most jarring conundrum of the entire cosmic dawn: the inexplicable speed of supermassive black hole seeds. We are talking about objects weighing millions or even billions of times the mass of our Sun, sitting at the hearts of galaxies that formed when the universe was barely a toddler. Standard physics suggests black holes grow by slowly feeding on gas and merging with other black holes over vast stretches of time. Yet we have found quasars, such as the famous ULA's J 1342+0928, which already housed a black hole weighing 800 million solar masses just 690 million years after the Big Bang. That rate of growth feels like a cosmic cheat code, breaking all the rules of established physics. How could something so large possibly form so quickly? Cosmologists have proposed 3 main theoretical models for these impossibly fast starting points, or black hole seeds. The first is called the direct collapse model. This scenario bypasses stellar evolution entirely. Instead of a star dying to form a black hole, a massive cloud of primordial gas collapses almost instantaneously into a single black hole seed, potentially weighing 100,000 solar masses from the start. This gives the black hole a massive head start on its growth. Another model suggests the seeds came from the remnants of those giant, short-lived population 3 stars. When these behemoths died, they left behind seeds perhaps only tens or hundreds of solar masses. For these to reach billions of solar masses so quickly, they had to be feeding at an extreme, non-stop rate known as super-Eddington accretion. Finally, the third idea involves runaway stellar collisions in dense, early star clusters. Here, stars in a crowded young galaxy repeatedly crash into each other, merging into a single ultra-massive star that then collapses into a large black hole seed. Each model requires conditions that were unique to the violent, dense environment of the cosmic dawn. Finding a black hole already weighing 1 billion suns when the universe was less than 700 million years old stretches our current understanding of gravitational growth to its absolute breaking point. It demands that we either find a mechanism for incredibly rapid, efficient feeding, or we must prove that the universe created gigantic black hole seeds right out of the gate. This mystery is vital because these ancient supermassive objects directly shaped the evolution of their host galaxies and, ultimately, the fate of the universe. The formation of gigantic black holes and massive galaxies hinged entirely on invisible structures. This brings us to mystery number 8, the critical role played by dark matter halos. Dark matter does not emit or interact with light, yet it provided the gravitational scaffolding necessary for the first stars and galaxies to form. Without these massive, invisible clumps of matter, the ordinary gas in the early universe would have simply spread out, never collapsing enough to ignite fusion. The key debate centers on the minimum size of a dark matter halo required to actually host a star-forming galaxy. We know that the gas needed to cool and compress within these halos, but if the halo was too small, the gas would be too hot or escape too easily, preventing star formation. Cosmologists use concepts like the filtering mass and the Jeans mass to define these thresholds. The Jeans mass describes the minimum mass a cloud of gas must have to overcome its internal pressure and collapse under its own gravity. The filtering mass takes into account how the intense ultraviolet radiation from neighboring, larger galaxies can actually prevent gas from collapsing into the smaller, less massive halos. But here is where the process becomes deeply complex and non-linear. The feedback from those very first stars and protogalaxies violently complicated everything. When a giant population 3 star exploded in a supernova, or even during its life through fierce stellar winds, it released incredible amounts of energy. This energy could effectively clean out or heat up the gas within nearby, smaller dark matter halos, suppressing any chance of secondary star formation. Imagine lighting a small match in a dense forest. The heat and wind from that single flame could dry out or completely blow away the kindling in all the surrounding clearings. This destructive stellar feedback means that even if a small dark matter halo had enough mass to potentially form stars, the proximity of a massive early light source would sterilize it. Thus, the assembly process was highly selective. Only the largest, most shielded, and most massive dark matter halos could withstand the relentless cosmic interference and successfully birth a galaxy. Figuring out exactly where this tiny minimum star-forming threshold lies is essential to understanding the total number of galaxies that existed in the cosmic dawn. If the first dark matter halos were lucky enough to hold onto their gas, they still faced an immediate, deadly threat from within. Mystery number 9 centers on the devastating stellar feedback mechanisms unleashed by the death of the very first stars. When those magnificent population 3 stars, those giants made only of pure hydrogen and helium, reached the end of their brief lives, they exploded with an intensity the universe had never witnessed. We are talking about something called pair instability supernova. This specific type of explosion only happens to stars between roughly 140 and 260 solar masses. For these titans, the internal processes become so unstable that instead of simply collapsing, the entire star completely obliterates itself, leaving behind no remnant black hole or neutron star. The energy released is incomprehensible, vaporizing the star and injecting immense amounts of raw energy and momentum into the surrounding interstellar medium, or ISM. This violent end had a dual effect on the fragile young universe. First, it solved the purity problem. These stellar bombs were the universe's first factories for heavy elements like carbon, oxygen, and iron, enriching the once pristine gas with the building blocks necessary for future life. That element distribution is the ghost we mentioned earlier. the evidence that these stars existed, but the second effect was profoundly destructive. This injection of colossal energy acted like a cosmic shotgun blast, forcefully ejecting the remaining gas from its host dark matter halo. Imagine a young, growing galaxy as a bowl of gas. When a pair instability supernova exploded, it was powerful enough to completely empty that bowl, delaying any further star formation for millions or even hundreds of millions of years. This stellar feedback was one of the primary hurdles the universe had to overcome to build structure. It created self-regulating systems where a burst of star formation led to a violent explosion, which then shut down the star formation until the halo could slowly gather new gas. Understanding the precise timing and efficiency of this ancient stellar feedback is essential because it dictated the pace at which the cosmos matured, controlling the supply of light and heat for the era of reionization. The violence of stellar death introduced a profound change to the universe's chemistry. This brings us to mystery number 10, the origins of the first heavy elements, or as astronomers call them, metals. Every element heavier than hydrogen and helium, everything from the carbon in our bodies to the silicon in our planet, had to be forged in the fiery heart of a star and then scattered across space by an explosion. The universe began with almost nothing but primordial gas, and the sole factories producing these essential metals were those gigantic, short-lived population, 3 stars we discussed earlier. When they detonated in pair instability supernova, they were simultaneously destructive and creative, injecting the very first traces of carbon, oxygen, and iron into the pristine gas clouds. Now the mystery is how and where to find the chemical signatures of these first explosions. Since the stars themselves are gone, we are hunting for their direct descendants, stars that formed immediately afterward out of gas that contained just the barest hint of metal contamination. These are known as ultra-metal-poor stars, often classified as population 2 stars. These stellar fossils reside today in unexpected places, mostly lurking in the faint reaches of our own Milky Way halo or in tiny satellite dwarf galaxies orbiting our own. Astronomers use powerful telescopes to analyze the light or spectral signature of these ancient population 2 stars. If a star formed from gas that was polluted by a pair instability supernova, its spectrum will show a remarkably unique and distinct pattern of elements. For example, some stars show an extremely high ratio of elements like carbon and oxygen compared to iron, a pattern that points directly back to certain types of massive early explosions. Finding enough of these chemically pristine stars and mapping the precise elemental ratios within them allows scientists to reverse engineer the nature of the population 3 star that died to create that metal mix. It is like finding a tiny, unique fleck of paint on an ancient artifact and realizing that single fleck holds the key to identifying the entire lost civilization that produced it. The quest for these chemical ghosts is not merely academic. It provides the only direct evidence we may ever find of the unique physics and immense power of the universe's ultimate stellar pioneers. The violence of those first stellar explosions essentially created a shattered cosmic landscape. Before reionization was complete, the universe was not uniformly cleared. Instead, it was an incredibly complex, constantly shifting patchwork of transparent, ionized bubbles expanding into a surrounding sea of opaque, neutral hydrogen fog. This dynamic structure brings us to mystery number 11, the great challenge of mapping the fine, small-scale structure of that neutral hydrogen. Identifying the size and distribution of these ionized bubbles is absolutely critical because it reveals the nature of the light sources that created them. If we found many huge, early bubbles, it would signal that distant, powerful quasars were the primary drivers of reionization. Conversely, finding a multitude of small, overlapping bubbles would point toward the more numerous, but individually fainter, proto-galaxies as the main engines. Understanding this cosmic geography is currently the final frontier in observational cosmology. The challenge is that this neutral hydrogen gas, the fog itself, is almost completely invisible to optical telescopes like the James Webb Space Telescope. We cannot see it light up, but we can detect its characteristic radio signature, the 21-centimeter line. This 21-centimeter line is a faint radio wave emitted when the spin of a hydrogen atom's electron flips. Every atom of neutral hydrogen in the early universe was emitting this faint signal, creating a kind of cosmic hum. The signal is incredibly weak and has been stretched dramatically by the expansion of the universe, meaning it reaches us today at extremely low radio frequencies. Detecting this radio hum is like trying to hear a single whisper from across a vast stadium while fireworks are going off. This is where future, massive low-frequency radio arrays, such as the Square Kilometre Array or SKA, come into play. These instruments are designed to work together as continental-scale virtual telescopes, dedicated solely to mapping the three-dimensional structure of the neutral hydrogen gas during the cosmic dawn. By mapping the 21-centimeter line, scientists expect to create the first true maps of those ionized bubbles, showing exactly where light had cleared the fog and where the darkness still reigned supreme. This data promises to finally reveal the small scale inhomogeneities, the bumps and valleys in the reionization process, giving us the definitive answer about who exactly flipped the universe's light switch. Mapping that neutral hydrogen hum will reveal a universe that was far from homogeneous. Mystery number 12 asks why the process of reionization was so profoundly non-uniform. The transition from darkness to light was not a smooth, even process that progressed simultaneously across the entire cosmos. Instead, evidence strongly suggests reionization was patchy, unfolding like Swiss cheese with holes of transparency forming and expanding within a solid block of darkness. These transparent holes, the ionized bubbles, did not appear randomly. They began forming in the regions of the early universe that were already the densest. Density is everything in cosmology because it dictates where gas gathers and gravity takes hold. The densest regions collected more matter and thus housed the most massive, most active protogalaxies and the earliest supermassive black holes, are sources of ionizing photons. These powerhouse regions were the first to flood their surroundings with ultraviolet light, stripping electrons from the hydrogen atoms immediately around them and carving out large, spherical bubbles of clear space. As the neighboring light sources grew stronger and multiplied, these bubbles expanded outward and eventually collided, merging into much larger, clear volumes. The vast empty voids of the early universe, where gas was sparse and gravitational collapse was slow, retained their neutral hydrogen fog the longest. They sat patiently in the darkness while the bright, dense neighborhoods around them celebrated constant, powerful bursts of star formation. This non-uniformity is a massive headache for cosmologists trying to create accurate computer simulations of the cosmic dawn. It means that to accurately model the process, we cannot simply assume a fixed date for reionization across the universe. We must account for these large-scale structure formation biases, explaining why some regions matured hundreds of millions of years before others. The very patchiness of cosmic reionization is a direct fingerprint of how large structures first formed, confirming that even in its infancy, the universe was already playing favorites with density. The visibility of those first star systems hinges on a profound cosmic contradiction. This contradiction is mystery number 13, the Lyman alpha emission problem. To trace the birthplaces of stars in the early cosmos, astronomers look for a very specific spectral signature called Lyman alpha emission. This is a bright, ultraviolet light produced when electrons in hydrogen atoms drop down to their lowest energy state. Because hydrogen is the most abundant element in the universe, Lyman alpha is an incredibly effective tracer of active star formation, acting like a neon sign for young galaxies. But for this signal to reach our telescopes, it has to travel through the vast cosmic space between the galaxy and us. During the cosmic dawn, That space was still filled with the opaque neutral hydrogen fog. The paradox is simple. Neutral hydrogen gas is incredibly efficient at absorbing or scattering Lyman alpha light. If the intergalactic medium was indeed a vast, dense sea of neutral hydrogen, then those Lyman alpha signals should be almost entirely swallowed up, meaning we should not see any such galaxies at high redshift. Yet we do. Astronomers are finding vibrant, active Lyman alpha emitters, or Li, back when the universe was still mostly shrouded in the neutral fog. How did their light punch through that heavy blanket? This observation tells us that the galaxies we see must be residing in locally cleared environments, essentially sitting in their own private ionized islands. These islands are the bright centers of the patchy reionization process, the regions that cleared the fastest because they were the densest and most active. The sheer amount of Lyman alpha light escaping these galaxies suggests they were not only powerful star producers, but they were also incredibly efficient at creating large bubbles of transparent, ionized gas around themselves. Furthermore, the light that did escape may have relied heavily on powerful outflow mechanisms. Imagine the massive stellar winds and supernova explosions inside the galaxy, literally blasting the surrounding gas away, creating a clear channel for the photons to travel through the galaxy's own interstellar medium. If these early galaxies were hyper-violent, they could have cleared a direct path for the Lyman alpha signal to escape into the already ionized bubble surrounding them. Ultimately, the survival of these faint, ancient Lyman alpha signals is a direct measure of how deeply embedded a galaxy was within the newly cleared regions of the cosmos. Every Lyman alpha emitter we find is another day, a point in mapping the size and location of those first islands of light. The search for that 21-centimeter hum has already delivered one of the most stunning cosmic contradictions of the decade. This brings us to mystery number 14, the jaw-dropping anomalies found in the 21-centimeter signal by the EDGES experiment. EDGES stands for Experiment to Detect the Global Epoch of Reionization Signature. In 2018, scientists working with this relatively small radio telescope in a remote desert in Australia announced a result that immediately sent shockwaves through the physics community. They detected a distinct absorption dip in the 21-centimeter signal, a detection that means we were successfully measuring the neutral hydrogen gas of the cosmic dawn. But this dip was not only about the timing of the signal, it was about its strength. The EDGES team found an absorption signal that was twice as deep as standard cosmological models predicted and appeared much earlier than expected, back when the universe was only about 180 million years old. A deeper absorption dip means that the neutral hydrogen gas of the intergalactic medium, the IME, was unbelievably cold. For the first time, we had a direct temperature reading of the early universe, and it was frigid, possibly only 3 kelvins, or about -454 degrees Fahrenheit. This is where the physics breaks down. Standard models, which include the heating effects from early stars and X-rays we discussed earlier, predict the IGM should have been significantly warmer by that time. To achieve a temperature this low, the process that made the hydrogen gas capable of absorbing the background radiation, the Walthysen field coupling, had to be incredibly efficient. Furthermore, the gas itself had to be cooled through some unknown, highly effective mechanism. This anomaly forces cosmologists to consider 2 extraordinary possibilities. The first is that the very first population, 3 stars, were far more efficient and formed much earlier than assumed, completely overwhelming the early universe with their intense ultraviolet light before the warming X-rays could take effect. The second and more radical possibility suggests entirely new physics at play. Maybe the primordial hydrogen gas was being cooled by an interaction with dark matter itself. If a type of dark matter particle existed that was slightly cooler than the gas and could interact gravitationally with it, it would act as a cosmic refrigerator, drawing the temperature of the hydrogen down to these impossibly low levels. If the EDGES result is confirmed by future experiments, It would simultaneously reshape our timeline of early star formation and provide the first direct evidence of particle physics beyond the Standard Model. It is the ultimate cold case, the mystery of the unexpected deep freeze of the cosmic dawn. The mystery of the cosmic cold spot leads us to a population of sources that might have warmed and cleared the universe without us ever seeing them. This is mystery number 15, the critical role played by faint, nearly undetectable galaxies. Think back to the sheer energy needed to reionize the entire cosmos. If we conducted a census of all the most powerful, brightest sources we have observed so far, the luminous quasars and the massive protogalaxies, that total energy budget simply does not add up. If we only rely on the bright light sources, the universe should still be shrouded in neutral fog. This profound deficit tells cosmologists that the bulk of the necessary ionizing radiation must have come from a massive, hidden population. We call these cosmic minnows. These faint galaxies are individually far too dim to be picked up by even the James Webb Space Telescope, but their collective power, multiplied across tens of billions of tiny systems, provides the missing energy. Standard cosmological models predict the universe should be teeming with these miniature star systems, each forming stars at a modest but steady pace. They reside in the smaller, less massive dark matter halos that were far more numerous than the massive halos hosting the bright, rare galaxies. Why are these minnows so important? They solve the problem of distribution. While a massive quasar blasts a huge bubble of ionized gas in one spot, these numerous faint galaxies would have spread their light out evenly, creating a more porous, overlapping structure of bubbles that could more efficiently merge to clear the universe. Furthermore, their small size may have been an advantage in the escape fraction problem. It is much easier for ionizing photons to escape a tiny, less dense galaxy than it is to punch through the thick, turbulent gas cloud of a massive system. These cosmic minnows likely acted as hyper-efficient, small-scale ionizers. Scientists are now developing observational techniques that rely on statistical analysis rather than direct viewing, looking for the telltale collective imprint of these faint sources on the background light. Identifying the true number and efficiency of these cosmic minnows is vital, because they represent the quiet, hardworking majority that successfully flipped the universe's light switch. Identifying the quiet, hardworking majority of faint galaxies leads us to a fundamental constraint on the whole process. How small could a clump of matter be and still successfully form a star? This is mystery number 16, the minimum mass for star formation. In the primitive universe, gas was almost entirely hydrogen and helium, and it was hot. For gravity to successfully pull this gas together to form a star, the cloud had to first shed its immense heat. This required cooling mechanisms. In the early universe, where no complex molecules like water or carbon monoxide existed yet, the only available coolant was molecular hydrogen, the simplest molecule, H2. When two hydrogen atoms bonded, that molecular hydrogen acted as a thermostat, efficiently radiating away heat and allowing the gas cloud to collapse. This process determined the mass threshold. If the cloud was too small, it could not gather enough molecular hydrogen to cool efficiently, and it would simply dissipate or remain too hot to collapse. However, the universe did not allow this process to occur peacefully. The cooling was constantly threatened by the intense ultraviolet radiation field generated by the first massive stars and protogalaxies. This leads to the concept of photodissociation. The powerful UV light from neighboring galaxies could entirely destroy molecular hydrogen, essentially smashing the H2 bonds apart before they could do their job as coolants. If the molecular hydrogen was photodissociated or broken up, the gas cloud instantly lost its ability to cool. This raised the required mass threshold dramatically. A dark matter halo that might have been able to form a star on its own in an isolated spot would be completely sterilized if it sat near a giant, actively star-forming neighbor. The UV background effectively suppressed star formation in the vast majority of smaller dark matter halos, delaying the cosmic minnows we discussed earlier. Finding the true minimum mass needed for star formation, balancing the internal cooling against the external, destructive UV background, is essential because it dictates the total number of galaxies the universe could possibly produce. If the UV background was too strong, it locked away huge potential populations of stars. If it was weaker, the universe would have been overflowing with small, faint galaxies that completed reionization much faster than we currently estimate. The fierce ultraviolet light from the first stars was not the only game changer in the cosmic dawn. If the universe needed massive, efficient heating to solve the deep freeze problem, it needed X-rays. This brings us to mystery number 17, the profound impact of those earliest X-ray sources. Unlike the ultraviolet photons produced by young stars, which struggled to escape their host galaxies and were easily absorbed by the neutral hydrogen fog, X-rays were cosmic penetrators. These high-energy beams could travel immense distances through the intergalactic medium, almost unimpeded, reaching deep into the neutral hydrogen far from any galaxy. They were the universe's ultimate long-distance heaters. Where did these powerful X-rays originate? The most likely suspects are twofold. First, they streamed from the accretion disks of those early supermassive black holes we discussed, the ones gorging themselves on gas at impossible speeds. When matter accelerates to near light speed before falling into a black hole, it emits intense high-energy radiation, including X-rays. The second source comes from less spectacular but more numerous objects called high-mass X-ray binaries. These are close-knit stellar pairs where a massive young star orbits an invisible partner, which is usually a neutron star or a stellar mass black hole. As the massive star sheds material, its companion greedily pulls that gas inward, heating it to millions of degrees and releasing a tremendous, steady stream of X-rays. The effect of this pervasive X-ray background was subtle but crucial, because X-rays do not immediately strip electrons from hydrogen atoms, they simply deposit energy into the surrounding gas. This process preferentially heated the neutral hydrogen, gently raising the temperature of the gas over vast stretches of the cosmos. This heating mechanism offers a potential solution to the shocking cosmic cold spot revealed by the EDGES experiment. If these early X-ray sources were abundant and active enough by the time the universe was only 200 million years old, they could have slowly warmed the intergalactic medium precisely as the models demand. We are trying to determine if these early cosmic heaters were numerous and powerful enough to counteract the cooling effects of that quickly expanding universe, ensuring the gas was warm enough for structure formation to proceed as we observe it in later epochs. Identifying the density and luminosity of the first X-ray sources is like finding the universe's oldest, hardest working radiators. The universe's oldest and most luminous objects hide a stunning chemical signature. This brings us to mystery number 18, the baffling metallicity of the earliest quasars. We are talking about cosmic environments that should have been pristine, made only of hydrogen and helium, yet the gas clouds surrounding those ancient high-redshift quasars are already heavily polluted with metals. Examining the light or spectra that streams from these blinding centers of young galaxies shows that elements like carbon, oxygen, and iron are present in surprising abundance. This is a profound contradiction. If a quasar lights up when the universe is only 700 million years old, how could the material it is currently feeding on already be chemically mature? It implies that the local environment surrounding that supermassive black hole had already witnessed multiple generations of massive stars live and die, explode in supernova, and scatter their heavy element seeds across space. For this level of metal richness to exist so early, the process of stellar birth, life, and death had to be incredibly rapid and hyper-efficient. Simple models of cosmic evolution suggest this process should have required billions of years, allowing gas to slowly collect, form stars, wait for those stars to explode, and then give the resulting metal-rich gas time to settle before the next generation of stars could form. But the quasar evidence shows this all happened in an astronomical blink of an eye. The material they are consuming is not the pristine, primordial gas we expected. It has already been processed and refined by stellar evolution. This means that the dark matter halos hosting these earliest quasars must have been the ultimate cosmic factories, collapsing gas, forming colossal population 3 stars, triggering their violent deaths, and utilizing the enriched gas for the next cycle of star formation almost instantaneously. We are forced to ask if the earliest massive galaxies were simply stellar machines operating at impossible speeds, or if the initial population, 3 stars, produced and scattered heavy elements with far greater efficiency than current simulations predict. This rapid chemical enrichment remains one of the strongest pieces of evidence that structure formation in the cosmic dawn was far more accelerated and violent than anyone initially theorized. The evidence of rapid chemical enrichment forces us to confront the true ancient frontier. Mystery number 19 involves probing the epoch of first light, the time before the cosmic dawn truly began. We are talking about the universe at an age far earlier than any of the quasars or protogalaxies we have mentioned so far, back when the universe was only tens of millions of years old. This is the true cosmic dark ages, a time before Redshift 20, when the very first energy sources were just flicking on. This era remains virtually unobserved, a scientific blank slate stretching deep into the past. Look at all the amazing things the James Webb Space Telescope has shown us. It is the most powerful optical instrument ever built, but even Webb cannot penetrate this far back. The light from that era is simply too stretched by the expansion of space, moving it completely out of the optical and near-infrared range and into the incredibly long wavelengths of low-frequency radio waves. This means that once again, the 21-centimeter signal is our only viable probe. If we can detect the faint radio hum of neutral hydrogen gas from that unbelievably distant time, it would tell us exactly when and where the very first pockets of heat and light appeared. Yet the challenge of detecting this signal is monumental, a technical hurdle so difficult it sometimes feels impossible. The problem is contamination. To see that faint, stretched-out 21-centimeter signal, which might be only a micro-Jansky in strength, we must look directly through the most powerful source of radio interference in our entire sky, our own Milky Way galaxy. The Milky Way is a churning factory of synchrotron radiation, a bright radio glow produced by electrons spiraling in magnetic fields. This galactic foreground contamination is hundreds of thousands of times brighter than the signal we are trying to detect. It is the equivalent of trying to see a single candle flame on the moon while staring directly into the midday sun. Scientists are building massive, remote radio arrays like the Hydrogen Epoch of Reionization Array, or HERA, specifically to overcome this challenge. They rely on complex algorithms and precise modeling to mathematically subtract the foreground contamination, hoping to peel back the layers until only that pristine, ancient 21-centimeter signal remains. Detecting the radiation from that true epoch of first light would be like discovering the first sentence written in the book of cosmic history, revealing the precise moment the universe began its transformation toward light-filled existence. Peeled back layers of the early universe reveal a fragile cooling mechanism. This leads us to mystery number 20, the precise physics governing the formation and destruction of molecular hydrogen, or H2. We know that H2 was fundamentally the most important compound in the early universe, the cosmic thermostat that controlled the birth of the very first stars. For a cloud of primordial gas to collapse under its own weight, it had to radiate away heat incredibly efficiently. Alone, individual hydrogen atoms cannot do this very well, But when two hydrogen atoms bond to form molecular hydrogen, the molecule becomes an excellent radiator of thermal energy. Without H2, the gas remains too hot and too pressurized to collapse, and no stars can form. The difficulty lies in determining the universe's chemical balancing act. How efficiently did this H2 form in the primitive gas clouds, and how quickly was it annihilated by the rising tide of ultraviolet light? H2 is notoriously fragile. The very powerful UV radiation streaming from the first stars and protogalaxies, even those stars that formed in neighboring halos, could easily photodissociate it, smashing the bond between the two hydrogen atoms. This destruction was instantaneous and deadly for star formation. The puzzle for cosmologists is finding the equilibrium point. If H2 formed too slowly, star formation would be delayed indefinitely. If, however, the rate of H2 destruction by the increasing UV background was higher than the rate of its formation, the entire process would stall. This balance was likely chaotic and localized. In the true voids of the early universe, where UV light was scarce, H2 could form and allow smaller star-forming clouds to collapse. But in the dense neighborhoods, where massive star formation was already underway, the intense UV radiation created a sterile zone, preventing H2 formation entirely across billions of cubic light-years. Scientists use complex simulations to model this chemical feedback loop, trying to establish the exact conditions under which a gas cloud could successfully shield its precious H2 molecules long enough to ignite fusion. The outcome of this struggle between creation and destruction dictated the minimum mass required for star formation, essentially controlling the density and timing of the entire cosmic dawn. The chaos of creation and destruction left behind stubborn pockets of darkness. This leads us to mystery number 21, the critical role played by Lyman limit systems. These are not merely random clumps of gas. They are the most dense, resilient pockets of neutral hydrogen that manage to survive the aggressive march of reionization for long periods. Think of them as cosmic fog banks floating in an otherwise clear, ionized sea. They represent the final, hard-to-clear remnants of the universe's dark ages. Astronomers detect these systems by using the light from extremely distant quasars. When quasar light travels across the cosmos toward us, it passes through everything in its path. If that light encounters a dense pocket of neutral hydrogen, atoms within that pocket absorb the light at specific ultraviolet wavelengths, creating sharp, prominent dips in the quasar's spectrum. These dips are the signature of a Lyman limit system, a direct measurement of neutral gas that has not yet been cleared. The observation of these dense survivors is crucial for mapping the boundaries of the reionization process late in the cosmic dawn. Why did these specific pockets survive the ionization onslaught? Their persistence likely stems from immense density. If a gas cloud was dense enough, even the fierce ultraviolet light from surrounding galaxies could not penetrate its core. The outer layers might be slowly ionized away, but the inner core remained shielded, preserving its neutral state. By studying the number, density, and size of these Lyman limit systems at various points in cosmic history, scientists can trace the boundaries between the fully ionized regions and the last bastions of the neutral fog. The rate at which the number of these systems dropped indicated how quickly the ionization process finished. If we find many massive, dense systems surviving late into the universe's first billion years, it suggests that the sources of ionizing light were either less powerful or less effective than we thought. Conversely, a rapid decline in their numbers points to explosive, highly efficient light sources. These cosmic fog banks are the ultimate witness to the end of the Dark Ages, providing a direct measurement of the universe's transparency at the moment the lights finally completed their turn on. The very first stars did not merely flicker on. They likely burst forth in crowded, spectacular displays. This leads us to mystery number 22, the question of whether the first stars formed in isolation or within dense, massive star clusters. Current theoretical evidence strongly suggests that the environment of the cosmic dawn was simply too chaotic and dense for solitary stars to form. In the massive dark matter halos that first collected gas, the primordial material cooled so rapidly and efficiently that it collapsed into exceptionally dense filaments and knots. Imagine the early universe not as a gentle nursery, but as a hyper-pressurized chamber where gas was forced together at an incredible rate. Within these extremely dense knots, the gas would fragment not into singles, but into numerous, closely packed stellar embryos. This resulted in the birth of the first stars within tight, massive clusters. These were not the leisurely, dispersed open clusters we see in the Milky Way today. These were super-dense, gravitationally violent environments where the stars were born practically touching each other. The immediate consequence of this high density was constant dynamical interaction. These newborn population 3 stars, already immense, began to strongly influence their neighbors. This proximity led to frequent stellar mergers, where 2 stars literally collided and combined to form an even more massive object. These mergers could have quickly pushed some stars past the pair instability threshold, ensuring their violent system-clearing end, or they could have created those short-lived ultramassive stars that collapsed directly into large black hole seeds. The existence of these dense, early clusters is a critical piece of the puzzle because it explains the extreme phenomena we see elsewhere. For example, the rapid growth of supermassive black holes could have been jump-started by runaway stellar collisions in the core of these clusters. Furthermore, the immense cumulative ultraviolet output from hundreds of closely packed, giant stars would have amplified the ionization power of the first galaxies, helping to carve out those early, large ionized bubbles much faster than an equal number of dispersed stars could manage. Pinpointing direct evidence of these ancient, dense clusters remains elusive, but their theoretical necessity to explain the observed extreme mass and efficiency of early cosmic structures makes them a defining feature of the cosmic dawn. The intensity of those first light sources demands we understand the flow of gas that fed them. This brings us to mystery number 23, the dominance of cold, dense accretion streams. We know that the first massive galaxies, the ones that grew surprisingly fast, required a steady, massive influx of gas to sustain their phenomenal star formation rates. In standard models of galaxy formation, gas is believed to fall into the dark matter halo, where it is shocked and heated to millions of degrees before it slowly cools and settles onto the galactic disk. This hot mode of accretion is efficient, but it is too slow to account for the astonishing pace of star formation observed in those high redshift, shockingly mature galaxies. Instead, cosmologists propose that the early universe was dominated by cold flow accretion. Think of the dark matter web of the universe as a massive, 3-dimensional spider web. Gas flowed rapidly along the densely woven filaments of this web, streaming into the centers of the dark matter halos along narrow, concentrated channels. Because this gas traveled along the filaments, it avoided the broad, violent shock heating that would normally occur and remained relatively cold and dense, bypassing the slow cooling phase entirely. This cold, dense supply of gas acted like a super-efficient pipeline, delivering massive quantities of fuel directly to the galactic core. This meant the earliest protogalaxies did not have to wait for hot gas to cool down leisurely. They could devour huge amounts of ready-to-use fuel almost instantly. These powerful, continuous streams allowed galaxies to sustain burst after burst of highly efficient star formation, rapidly building the stellar mass and the chemical enrichment we see in those ancient quasars. Identifying these cold flow streams directly is incredibly challenging, as the gas is too faint and too quickly consumed to be easily observed. However, the evidence for their existence is compelling. They are the only mechanism currently theorized that can explain the impossible abundance and maturity of the largest galaxies formed less than 1 billion years after the Big Bang. The rapid assembly of the first cosmic structures raises a fundamental question about the very fabric of the early universe. This is mystery number 24, the true nature and evolution of the primordial magnetic fields. Today, we know that magnetic fields permeate galaxies and the vast, empty space between them. They are crucial for star formation, regulating the flow of gas, and even influencing the propagation of cosmic rays. But where did these fields originate, and how strong were they in the cosmic dawn? Magnetic fields were not created during the Big Bang. They had to be generated later through complex, small-scale processes in the dense early universe. Cosmologists debate two main origins. The first is the battery mechanism, where the rotation and turbulence of star-forming regions and the plasma around black holes generate tiny seed magnetic fields. These initial fields are incredibly weak, but they are then amplified by chaotic motion and galactic rotation, a process called the turbulent dynamo. The second possibility is known as magnetogenesis, where the fields are created by physics that existed even before the first stars, perhaps during those violent interactions or phase transitions in the very early universe. The strength of these fields in the cosmic dawn is critical because it fundamentally influences structure formation. If the magnetic fields were already relatively strong, they could have helped regulate the collapse of those cold, dense accretion streams, preventing gas from collapsing too quickly and fragmenting into smaller, less massive stars. Conversely, if the fields were too weak, they would have had little impact on the massive, rapid collapse of the first gas clouds. The only way to probe these ancient fields is through indirect observational evidence, specifically by looking for the subtle effects they have on the light from extremely distant quasars. When quasar light travels through a magnetized medium, its polarization can be subtly twisted, an effect known as Faraday rotation. By measuring this rotation in light from the most distant quasars, astronomers are trying to gauge the strength of the magnetic fields that existed in the intergalactic medium during the cosmic dawn. Finding a surprisingly strong magnetic field this early would revolutionize our understanding of plasma physics and structure formation, proving that even the empty space of the newborn universe was not truly empty. The accumulated evidence of extreme densities, violent feedback, and impossible growth leads us to the final mind-bending mystery of the cosmic dawn. This is mystery number 25, the ultimate challenge of simulating the universe's infancy. To solve all the mysteries we have discussed, from the minimum mass for star formation to the escape fraction of photons, scientists rely on complex computer models. These cosmological simulations, such as the famous Illustris and Millennium runs, attempt to recreate the evolution of the universe from the Big Bang to the present day. But precisely because the cosmic dawn era is so sensitive to small factors, simulating it accurately is an overwhelming task. Every process is intertwined. The formation of a single population 3-star dictates the chemical enrichment and future cooling of its entire neighborhood, which in turn influences the efficiency of the ionizing light, which dictates when and where the next star can form. This means that these processes are non-linear, unpredictable, and require immense computational power to model simultaneously. The difficulty lies in the sheer range of scale. To accurately simulate the large-scale structure of the universe, the simulations must cover hundreds of millions of light-years, but to capture the essential physics of star formation, they must model regions smaller than a light-year, tracking individual molecular hydrogen clouds. Bridging this enormous gap between the cosmic web and the birth of a single star, known as the dynamic range problem, is where most simulations fall short. If a simulation slightly underestimates the efficiency of X-ray heating or overestimates the destruction rate of molecular hydrogen, the results for the entire reionization timeline can be wildly inaccurate. The ultimate challenge is to create a single, massive simulation that can faithfully reproduce the incredibly low temperatures seen by edges, the existence of massive early galaxies seen by Webb, and the inexplicable speed of supermassive black hole growth, all while accurately matching the final timeline of cosmic reionization. When scientists finally achieve that unified model, we will have truly solved the 25 mysteries of the cosmic dawn and understood how the entire universe got its start. The ultimate challenge of simulating the universe hinges on understanding one geometric question: were the first ionized bubbles of light spherical, elongated, or highly irregular? The shape or morphology of these clearing bubbles is far more than a simple cosmic detail. It is a direct fingerprint left by the light sources that created them. If reionization was primarily driven by a few extremely bright, distant quasars, we would expect to see very large, roughly spherical bubbles. A single, powerful quasar could blast ultraviolet light equally in all directions, hollowing out a vast, symmetrical volume of neutral hydrogen. Conversely, if the process was dominated by the numerous, individually faint protogalaxies, the cosmic minnows we discussed, the resulting bubbles would be much smaller, overlapping, and highly irregular. In this scenario, the formation of the ionized regions would follow the intricate filamentary structure of the cosmic web. Imagine a vast, dark field where light sources are scattered across different depths. A single floodlight creates a perfect circle of light, but hundreds of small, uneven flashlights create a far more complicated, patchy mosaic. The true geometry of these bubbles will validate or refute every major simulation of the cosmic dawn. For instance, if the cold accretion streams were truly dominant and pulled gas into galaxies along narrow channels, the ionized regions might be elongated, following those same dense filaments. The only way to truly map this three-dimensional geometry is through those future 21-centimeter observations. By measuring the radio signal of neutral hydrogen at incredibly high resolution, observatories like the Square Kilometre Array will be able to resolve the exact boundaries between the dark, neutral gas and the clear, ionized plasma. If those observations reveal a universe initially cleared by huge, spherical voids, it means the bright quasars won the day. If they reveal chaotic, small-scale complexity, it confirms the quiet industry of the faint protogalaxies. This mapping expedition is critical, as the size and shape of these bubbles provide an undeniable test of whether our current models of star formation and light escape are truly accurate. The cosmic landscape was transformed not just by light, but by an explosion's deadly timing. We turn now to mystery number 25, the precise timing of the very first metal-free supernova. We know the magnificent pure population 3 stars lived fast and died young, detonating in those pair instability explosions that solved the universe's purity problem. But pinpointing the exact moment these events began injecting the first heavy elements or metals into the primordial gas is absolutely crucial. This timing sets the initial metal budget for every subsequent generation of stars and galaxies, fundamentally influencing how quickly the universe became chemically rich. If the first supernova happened very early, within the first 100 million years, the metal enrichment was widespread and rapid, accelerating the formation of normal, metal-containing stars. If they were delayed, the pristine, metal-free era lasted longer, slowing down cosmic evolution. Since we cannot directly observe these ancient explosions, we must rely on their ghosts scattered throughout the Milky Way today. This evidence comes in the form of extremely metal-poor stars, often called EMP stars, lurking in the faint reaches of our galaxy's spherical halo. These rare stellar fossils are essentially the direct descendants of the population 3 stars. They formed from gas clouds that were contaminated by just a single, isolated supernova blast. Astronomers search diligently for these EMP stars because their chemical composition is a perfect snapshot of the elements produced by the very first stellar deaths. Analyzing the light from these stars is like a forensic investigation, matching the unique ratios of elements like carbon, oxygen, and iron found in the star's atmosphere to the theoretical output of a pair instability supernova. The challenge is finding enough of these needle-in-a-haystack stars to build a statistically meaningful timeline. So far, the evidence gathered from these stellar survivors suggests that the metal enrichment process began surprisingly fast, confirming that the population 3 stars came and went quickly and violently. However, finding even one EMP star with 0 detectable iron would be the holy grail, proving that it formed from gas that was enriched only by the very first, purest stellar explosions. Establishing the precise chronology of this violent metal enrichment is essential for building accurate models of galaxy evolution, proving exactly how soon the universe began seeding the necessary ingredients for planets and life. The ultimate challenge of simulating the universe hinges on understanding one geometric question: were the first ionized bubbles of light spherical, elongated, or highly irregular? The shape or morphology of these clearing bubbles is far more than a simple cosmic detail. It is a direct fingerprint left by the light sources that created them. If reionization was primarily driven by a few extremely bright, distant quasars, we would expect to see very large, roughly spherical bubbles. A single, powerful quasar could blast ultraviolet light equally in all directions, hollowing out a vast, symmetrical volume of neutral hydrogen. Conversely, if the process was dominated by the numerous, individually faint protogalaxies, the cosmic minnows we discussed, the resulting bubbles would be much smaller, overlapping, and highly irregular. In this scenario, the formation of the ionized regions would follow the intricate filamentary structure of the cosmic web. Imagine a vast, dark field where light sources are scattered across different depths. A single floodlight creates a perfect circle of light, but hundreds of small, uneven flashlights create a far more complicated, patchy mosaic. The true geometry of these bubbles will validate or refute every major simulation of the cosmic dawn. For instance, if the cold accretion streams were truly dominant and pulled gas into galaxies along narrow channels, the ionized regions might be elongated, following those same dense filaments. The only way to truly map this 3-dimensional geometry is through those future 21-centimeter observations. By measuring the radio signal of neutral hydrogen at incredibly high resolution, observatories like the Square Kilometre Array will be able to resolve the exact boundaries between the dark, neutral gas and the clear, ionized plasma. If those observations reveal a universe initially cleared by huge, spherical voids, it means the bright quasars won the day. If they reveal chaotic, small-scale complexity, it confirms the quiet industry of the faint protogalaxies. This mapping expedition is critical, as the size and shape of these bubbles provide an undeniable test of whether our current models of star formation and light escape are truly accurate. The cosmic landscape was transformed not just by light, but by an explosion's deadly timing. We turn now to one of the final mysteries, the precise timing of the very first metal-free supernova. We know the magnificent, pure population 3 stars lived fast and died young, detonating in those pair instability explosions that solved the universe's purity problem. But pinpointing the exact moment these events began injecting the first heavy elements, or metals, into the primordial gas is absolutely crucial. This timing sets the initial metal budget for every subsequent generation of stars and galaxies, fundamentally influencing how quickly the universe became chemically rich. If the first supernova happened very early, within the first 100 million years, the metal enrichment was widespread and rapid, accelerating the formation of normal, metal-containing stars. If they were delayed, the pristine, metal-free era lasted longer, slowing down cosmic evolution. Since we cannot directly observe these ancient explosions, we must rely on their ghosts scattered throughout the Milky Way today. This evidence comes in the form of extremely metal-poor stars, often called EMP stars, lurking in the faint reaches of our galaxy's spherical halo. These rare stellar fossils are essentially the direct descendants of the population 3 stars. They formed from gas clouds that were contaminated by just a single, isolated supernova blast. Astronomers search diligently for these EMP stars because their chemical composition is a perfect snapshot of the elements produced by the very first stellar deaths. Analyzing the light from these stars is like a forensic investigation, matching the unique ratios of elements like carbon, oxygen, and iron found in the star's atmosphere to the theoretical output of a pair instability supernova. The challenge is finding enough of these needle in a haystack stars to build a statistically meaningful timeline. So far, the evidence gathered from these stellar survivors suggests that the metal enrichment process began surprisingly fast, confirming that the population 3 stars came and went quickly and violently. However, finding even one EMP star with 0 detectable iron would be the holy grail, proving that it formed from gas that was enriched only by the very first, purest stellar explosions. Establishing the precise chronology of this violent metal enrichment is essential for building accurate models of galaxy evolution, proving exactly how soon the universe began seeding the necessary ingredients for planets and life. The accumulated evidence of extreme densities, violent feedback, and impossible growth leads us to the final mind-bending mystery of the cosmic dawn. This is mystery number 25, the ultimate fate of the cosmic fog. When the lights finally turned on across the entire universe, the intergalactic medium became almost completely ionized and incredibly hot. But was that process truly irreversible? The final key to solving reionization is ensuring that the process stuck. If the clearing of the cosmic fog was a permanent change, then the universe we see today should be completely transparent, which it is. However, scientists have to confirm there were no mechanisms that allowed the gas to slip back into darkness. This phenomenon is known as recombination cooling. While the intense ultraviolet light stripped electrons from hydrogen atoms, creating the ionized plasma, the gas atoms still had a chance to capture an electron back, thus recombining into neutral hydrogen. This recombination process is heavily favored in environments where the gas is both dense and can cool quickly. If a large pocket of ionized gas fell into a deep gravitational potential well, such as the concentrated center of a young galaxy cluster, it could compress rapidly. This compression might allow the gas to cool down enough to temporarily revert, or recombine, back into a neutral state. These dense pockets of neutral gas, even if they only existed for a short time, would have created temporary opacity, briefly shrouding localized regions. If recombination cooling was efficient enough, it might have stalled the complete clearing of the universe, forcing the ionizing sources to work even harder and longer to achieve full transparency. The fact that the universe did eventually clear completely tells us that the heating mechanisms must have been exceptionally robust. The X-rays and ultraviolet photons not only ionized the hydrogen, but they also kept the gas hot enough and sparse enough to prevent atoms from grabbing their electrons back. Proving that these temporary neutral pockets were rapidly and permanently cleared confirms the lasting impact of the cosmic dawn. It means the universe truly crossed a threshold, making the transformation from darkness to light a one-way, irreversible journey that defined modern cosmology. 25 mysteries define the cosmic dawn. They are all centered on one profound, singular question: how did our structured, luminous, and chemically rich universe emerge from that initial, featureless darkness? We began with the question of timing, trying to date the moment the lights truly turned on. That quest led us into the hunt for population 3 stars, to the impossible speed of supermassive black holes, and the shocking prematurity of the very first galaxies. Every enigma, from the deep cosmic cold spot to the missing light budget of faint minnows, paints a picture of a universe that matured far faster and far more violently than the gentle, slow climbing evolution once predicted. We now understand that the forces that shaped us, dark matter halos, stellar feedback, X-ray heating, and the fragility of molecular hydrogen were constantly engaged in a self-regulating, chaotic process that ultimately transformed cold, neutral gas into the clear, vibrant cosmic web we inhabit. The entire journey of the cosmic dawn era, boils down to finding the precise balance between the destructive light and the gravitational power necessary to build structure. The fact that the universe succeeded in clearing its fog is a testament to the immense power of those first light sources. Now, for the first time in history, we stand on the precipice of solving these epochal questions. The excitement in the cosmology community is palpable because we finally have the right tools in hand. The James Webb Space Telescope has already revolutionized our view of early galaxies, pushing us to constantly revise our timelines and assumptions about the speed of cosmic maturity. Webb's incredible infrared sensitivity allows us to capture the faint, stretched-out light from those shocking protogalaxies with unprecedented clarity. But Webb is only one part of the solution. The other, perhaps more critical, part lies in the next generation of massive radio arrays. Instruments like the Square Kilometre Array, or SKA, and the Hydrogen Epoch of Reionization Array, or HERA, are specifically designed to tackle the invisible. They are the tools built to detect the elusive 21-centimeter hum, allowing us to map the three-dimensional structure of the neutral hydrogen fog for the very first time. In the next decade, these radio arrays will peel back the layers of our galaxy's radio contamination to show us the size, shape, and evolution of those first ionized bubbles. This data will provide the undeniable test for every single theory we have discussed, confirming whether big quasars or small galaxies won the battle for reionization. As this new dawn of discovery breaks, the ultimate secrets of the universe's infancy are finally within reach. The transformation from cosmic dark ages to our bright modern universe is no longer a theoretical abstraction. It is a puzzle we are poised to solve. The 25 mysteries of the cosmic dawn are more than just astronomical puzzles. They represent the unwritten first chapter of the universe's life story. We started this journey in utter darkness, contemplating a pure cosmos made only of hydrogen and helium. The contradiction at the heart of the cosmic dawn is that this purity shattered so spectacularly fast. Who would have predicted that the absolute first structures born would be so violent, so massive, and so efficient? The existence of those shockingly premature galaxies seen by the James Webb Space Telescope and the impossible speed of supermassive black hole growth force us to rethink the entire timeline of cosmic history. Our quest for the elusive population 3 stars, those magnificent fleeting atomic giants, is a hunt for the ultimate stellar ghost. Their existence, proven by the ghost of chemical enrichment found in metal-poor stars today, links the Big Bang to everything that came later. We wrestled with the invisible forces that govern the process, from the gravitational scaffolding of dark matter halos to the fragility of molecular hydrogen, the cosmic thermostat. Perhaps the most baffling finding remains that deep cosmic cold spot, the anomaly found by the EDGES experiment, suggesting a physics beyond our current understanding. Every single mystery we have explored is interconnected, confirming that the universe accelerated its own development, transforming from a simple, predictable environment into the complex, structured web we inhabit today. Solving these riddles, finally determining the true escape fraction, mapping the geometry of the ionized bubbles, and simulating the exact sequence of events will not just fill in a gap in astronomy. It will fundamentally redefine our place in the cosmos, providing a clear origin story for our galaxies, our elements, and ultimately ourselves. Which of these 25 mind-bending mysteries, from the earliest X-ray heaters to the final fate of the cosmic fog, did you find the most compelling? Do you side with the big quasars or the tiny faint galaxies as the true drivers of reionization? Share your hypotheses and evidence in the comments below. If you want to keep exploring the deepest, strangest puzzles of the universe, make sure you hit that like button and subscribe for more deep dives into the greatest cosmic secrets.